In this video we understand further concepts related to vector and Cartesian equations to describe lines. And so you can see there the four subtopics we're going to treat in this video are listed below, and we have Cartesian form for a line in 3 dimensions. We go from a vector equation to Cartesian, and vice versa. We have a look at the reverse. We look at parallel and perpendicular lines, what happens there, the distance from a point out to a line, and describing line segments. So looking at the first subtopic, going from a vector equation to Cartesian form, so let's look at an example. We've got a line which is going through the point 5, -2, 4, and we know that it is parallel to the vector 2i minus j plus 3k. Now we can describe that using a vector equation, especially if we use this point, if we call it something like A, and we use the position vector, which would be OA, or just lowercase a. And as you know, we have the general form from our previous work with our general form for a vector valued function. We have A plus parameter t times d, where d is a parallel vector and A is a position vector. So let's use this. We know that that point is on the line, and because the line goes through it, so we can write, for this case we can write, whoops, that's an equal sign. We've got 5i minus 2j plus 4k, and look, this is irking me, and t outside of a vector that is parallel to this vector here, so the t parameter will take care of that. Now in general, if we have point P, and P is noted as, in general, as x, y, z, and P is on the line in question, which has the position vector r just mentioned there, we can see that xi plus yj plus zk equals 5i minus 2j plus 4k plus t outside of 2i minus j plus 3k. Or 5 plus 2t I plus -2 minus t j plus 4 plus 3t k. We get parametric equations, as you can see, for x, y, and z relating to t. So to find t, in the first equation to get t, we have to go x minus 5 over 2. On the second equation there for t, we have t equals -2 minus y, which is over 1. And for the third equation with z there, we've got z take 4 over 3. Just tidying that up, especially the middle term there. So t equals x minus 5 over 2, which equals times the top by -1 2 plus y over negative 1. It's one of the rare cases where you see a negative on the denominator, and z minus 4 over 3. We say that this is in Cartesian form right here. Because with 3D vectors you can't describe it with just a single Cartesian equation. Okay, so Cartesian won't do that with three-dimensional vectors, unlike two-dimensional. So you need, you can't get by with just a single equation. Now, if we go back the other way from Cartesian to vector, we just reverse these steps. So it's just the reverse. In summary, for 3D vectors, we have the following to note. So let's note it. We have 3D vectors. A line in 3D dimensional 3 space can be described in the following ways. Okay, so given that we've got a vector A, which is A1i, A2j, A3k added together, it's the position vector on point A, which happens to be on the line, and D is a vector that's known to be parallel, D1i, D2j, D3k, all added together. That's your vector equation, where T is the real numbers, parametric equations which support that, A1 plus D1t for x, y is A2 plus D2t, and z is A3 plus D3t. The Cartesian form, as we just saw above, you may wish to reverse the video to see the corresponding elements there. Comes out as you see there, there's 3 of those. We need the 3 for 3 dimensions, okay, and they're based on these given vectors here, and you'll be able to go back to a little way in the video and see how the values and the examples relate to this pattern here. So that's important. The vector equation, the parametric equations, and the Cartesian form for 3D. Now for parallel and perpendicular lines, we don't throw it all out. We actually use all of the stuff we know, but we just got a couple of things to remember as well. So if we have 2 lines, L1 and L2, and L1 is given by the position vector, the vector valued function R1, which is A1 plus TD1, and we've got L2 is R2 plus equals A2 plus SD2, where S is another real number. Notice how there's a distinction between S and T, but they're the real numbers. Okay, lines L1 and L2 are parallel if and only if D1 is parallel to D2. And it should make sense if we think about some of the diagrams we've seen before, and if we've got D1 as a vector going in that direction, and if we have another vector parallel to that, okay, its D2 needs to be parallel to D1. We'll have a closer look at that in a moment. For the lines L1 and L2 to be at 90 degrees perpendicular, their dot product, D1 and D2, need to come to 0. You know that's one of the properties of the dot product. So D1 dot D2 has to equal 0. So let's look at an example here. Line L has this vector equation, and find a vector equation of the line that goes through point A given that is parallel to the line. Okay, so it goes through that point and it is parallel to this given line with position vector R. Okay, so to answer part A there, I'm going to come up with the position vector A, which is I plus 3j plus 2k as our first step. Now we just noted just above there that for them to be parallel, D1 has to be parallel to D2. So this would take the place of D1, and a parallel vector is a scalar multiple, so what we could say then the let me just call this R2, if we call that one R1. So the vector then that is parallel, we'll call R2. So we would have that as I plus 3j plus 2k plus s using a different scalar outside of negative I minus 3j. Okay, so it's that vector with a different scalar denoted on the front will give us the parallel effect, and we crazy if we don't use this given information, because it's definitely on the line, so that gives us the position vector on the front there. So you can still see it's in that form of A plus TD as the rough form, as our general form for these things. Okay, so it's still in that rough form, but we've got a different position vector, and we've got a parallel situation, which means it's a scalar multiple of D, but to make it distinguished from the original one, which was given with parameter T, we have to put a different parameter on, but S is still, S is an element of R. Sorry about the squiggles. In part B, we've got to find a vector equation of a line that goes through that same point, but it's perpendicular this time to L. So it means it's perpendicular to the plane. Alright, so it's actually perpendicular to the plane that that L resides in. Okay, so it's not just perpendicular to the line, but the plane, because the lines travel on a plane, don't they? And I don't mean they're on a 747. All right, they travel in on a flat surface. Now, if we have a look at that that plane, this particular plane has a k value of 0, so it's actually the xy plane. Okay, so it's traveling. This one will be perpendicular to the xy plane. Therefore, we need to find a d. We're required to find a d then that's in this form d1i plus d2j. Okay, and as we just discovered, its k component is 0. It's perpendicular to that, negative I minus 3j. So what we have is, for your dot product, in this concept of perpendicular, dot products need to equal 0. So we basically have d1i plus d2j dotted with negative I minus 3j has to be equal to 0, and our dot product means that we'll go negative 1 d1 plus d2 times negative 3, or negative 3 d2. That equals 0. Negative d1 equals 3 d2. d1. So that's oh, wait on. Let me go back a step there. Might have said the wrong thing. So negative d, if we add 3d2 to both sides, that'll be positive. Alright, so I wrote the right thing and said the wrong thing. Negative 1 d1 equals positive 3 d2, so d1 equals negative 3 times d2. So for example, if we let, there's lots of solutions to this, so let's look at a simple solution. A simple solution, because there's lots of solutions to this. If we let d1 equal, say, 3, that would mean that d2 equals negative 1, and that's a solution. It works. Therefore, subbing that into up here, therefore d So we've got d1 I, so that would be 3, that was supposed to be a 3. 3I minus j is one possible vector. Hence, we've got a position vector with parameter s is the position vector of the point plus s times that d that we just achieved. If we have to find the distance from a point to a line, we can use a scalar product to find the distance from point to a line. A couple of examples that I've just sourced there. Find the distance to the line of r of t given there from the origin. So the distance from the origin to the line given by that position vector given there. So looking at a diagram is helpful here. So I've just sourced this diagram. This diagram is from a Cambridge text. It's not my property here, but I'm just using it quickly. And we have negative 1 minus 3j is parallel to the line, okay, because we can see that there. We look at the diagram, and along the line, the closest point to the origin will be metered out by a line perpendicular to the line PP dash. So OP dash and PP dash are perpendicular. So for a point on the line OP, which is called R of t, as you know, this one, we take the dot product, and basically we get 10t takes 7. So we need to match our result here because it's where the point P dash let me clarify that. So in general, the expression for the dot product of OP dotted with D is 10t takes 7. For the perpendicular case, that also has to be equal to 0 based on our definition of a dot product. Thus, it needs to be the case where 10t minus 7 equals 0, so t would be 7/10 in such a case. So, by substitution, then we can get this expression here, and so the distance from the origin to the line, we can calculate that using our usual method of calculating the distance. For the next one here, it's the same situation with point 132. A different diagram is needed, and we need to do some vector addition here to get the required point, vector AP, which we get here. We apply the same process, the general expression for the dot product, and then for the dot product to be equal to 0, we use a similar process to what we saw as above. Then to find the distance, we repeat that process that we mentioned. Lastly, describing line segments, we use a vector equation and we restrict the values of the parameter because a line segment is part of a line, therefore we need to restrict parameter t or whatever the parameter is. So here's an example of that. To finish things off, we've got A and B, and they've got position vectors A and B lowercase, and we need to show that the vector equation given there represents the line through A and B, which is quite straightforward. Let's do that first. So all we need to do is find AB, okay, and the line or the vector AB, and we've basically need to go B minus A first of all, and then use one of the points as the position vector. The point A given above there has been used in that capacity, so you can see that there. We've basically then, in our usual form, the TD part, which you see there, as you can see, it links to that there. So that's familiar. find the set of values of t together with this vector equation that we just found to describe the line segment AB. So we make t equal to 0 in the first instance because that is the start of AB. You see, d is dependent on the length of d is dependent on t. It comes from your starting point, which uses a position vector based on A. So that gives us a starting point for A. Now we need to find the values of t which gives B lowercase, okay, because that'll give us the position vector that relates to point B in the segment AB. And so writing that down, we need to equate these here. As you can see, now we know from the given information above what the position vector for B is. Remember, it was 2i minus 3k. So we've got that there, and we need to equate those there. So with a little bit of thinking, we can find that the answer is t equals 1. So the interval that it relates to is all values inclusive from 0 through to 1 will satisfy that. They'll be all the points that make up the line segment. And lastly, find the set of values of t together with the vector equation we found to describe the line segment AC. C is a given point, three-dimensional point there, where C is a point on the line AB. So this part we're doing now relates to the two above. So we need to find a value of t which gives this position vector OC. So we go to work on that. Now it must be the case that it satisfies the vector that we found before must satisfy 4i plus 8j minus 9k. So using the vector in this format here, it's pretty easy to solve, and we can get t equals 3, and so that would be our interval 0 to 3 inclusive.